Yeah, excellent. Welcome everybody. Lots of people in the new year, which is excellent to see. Who's here for the first time? Anybody who has not been before? 1, 2, 3, 4, 5. Well, welcome to you. You just wanted to come and check out Bloomberg? Then I don't blame you. It's pretty fantastic here, isn't it? So thank you very much to Bloomberg and to David and to Dietmar and to Frank and everybody else for helping us out in our hour of need. We do very much appreciate it. And yes, welcome to you guys as well. As you can see from this absolutely enormous thing behind me, this is session 4 of our little module we're doing about the standard library containers and algorithms. So if you're new to C++ completely, then today's session, to be honest, you might kind of go, whoa. But that's okay, because all our material, pretty much everything we've ever done is online and they're available if you want to go and look at it. So all these slides that you're going to see today, all of those from the previous sessions are on our GitHub site, all the PDFs, and our YouTube channel has all the videos going back, well, quite a long time now. So by all means, please do. If today just seems a bit scary, don't panic. It's a progression. So if you begin at the beginning, as a lot of the folks here have, then it's not so scary. I'll wait for a couple of minutes. Hello. Yeah, I didn't say that, didn't I? Happy New Year, everybody, and I hope you all had a nice Christmas. It seems it's like a week ago already. I've forgotten. Sorry about that. Sorry? Yeah. Oh, can you double check on that? Okay, everybody's settled. As we're saying, this is session 4 of our containers, algorithms, the STL module, talking about that part of the standard library. Before we begin, people who have been to these sessions know I put this up at the start. We like to hear from you. In particular, we've got this, there's a Slack channel. So Slack is like a chat application, it's quite heavily used by programmers. There is a CPP Lang Slack channel just for talking about the C++ language. And we've got our own room in there, which is #CPP London Uni. So it's technically invitation only, but it's not a very exclusive club. You just have to go to that URL and pop your email address in, and it will send you a link so that you can join us. Really recommend everyone sign up and join our room, and then we can chat to you. And the other thing is, Tom mentioned it already, but this is only half of what we do. So we have these sessions on Tuesdays where usually me, standing at the front, nattering on for a couple of hours. That's half of it. The other half is Thursday evenings, where we have more in-depth practice sessions. It's not like this, it's not lectures, it's not slides. It's opportunities for you to practice what you've learned. Which is it's even more important, much more important in fact, than coming to these. Because the only way to get better at programming is by practicing programming, right? So please do, if you can at all spare the time, come along on Thursday evenings. The sessions are usually run by Ollie. Most of the time, I'll leave you with an exercise or sort of homework to do on a Tuesday. And the Thursday sessions are a really good opportunity to do that in a group environment, to help each other, to ask for advice from experienced people. Please do come along. Okay. So, last time we were talking about iterators. Seems like a very long time ago now, doesn't it? 18th of December. So we're talking about iterators. And some of the basic operations that you can do on iterators. Well, we're talking about what iterators are and basic operations that you can do on iterators. And then we had a Christmas party. So if you weren't there, no, I'm sorry, you missed out. It was a riot, I tell you. Room full of C++ programmers, we know how to party. What's on the menu for this week? I actually cut it down from what I was going to do. I was going to do a bit more, but I thought I'd trim it a bit. But if we run out of time, I've still got the slides there, so never fear. So we're going to talk about iterator categories. This was something we didn't have time to fully go into last time around because we wanted to party. So we'll talk about it today, and then we're going to go on to talk about the standard containers. So the C++ standard library has, I think it's about a dozen different containers that you can use, you should use in your own programs. And I'm going to go through and tell you, not about all of them, but about the main ones, the main heavily used ones. Just give you a little sort of high-level overview. And then we've got an exercise where you can practice using a couple of these containers. Does that sound good? Louder. Yeah? Yes. There's literally 3 of you there, but I don't know. It's 7 o'clock. It's late. Anyway, it's been a couple of weeks. Let's just have a little bit of revision about iterators. So a very high level. Iterators are the glue that bind together the STL containers, which we'll talk about later, and the algorithms, which we'll probably talk about next week. Start talking about next week. So containers provide these things called iterators, and the algorithms operate on them. The algorithms use them. So to give a little example here, I've constructed a vector, one of the standard library's container types, constructed a vector of integers. I use this function standard begin to obtain an iterator to the start of the container. Can anybody tell me another way that I could get an iterator to the start of the container? Vec.begin, absolutely. So all the standard containers have member functions called begin and end, and a few other similar ones as well. Or there's this freestanding function, non-member function called standard begin, which you can also use. It does the same thing. So we obtain an iterator to the start of the container. We obtain an iterator to the end of the container. And then we pass these 2 iterators to an algorithm, in this case, standard sort. So this means we're calling this function sort, and we want it to sort everything from the beginning of the container to the end, sort the whole container. So after this, all being well, the vector is going to contain 1, 2, 3, 4, 5. And one of the things that's a bit different about C++, this STL thing, compared to perhaps if you've used other languages, is there's no one iterator type. There's no iterator base class that everything else, implements the interface of. Rather, this notion of an iterator is a generic concept, as it's called in the terminology. So something is an iterator if it does the things that an iterator should do. It's what's called duck typing. So if it looks like a duck and it walks like a duck and it swims like a duck, it's a duck. Right? So this uses duck typing. If something behaves like an iterator, then it is an iterator. There is no iterator base class. There is no, well, there is a standard iterator, but you shouldn't use it. There's no standard one iterator type. Every container implements its own iterator types. Is all this coming back to you now slowly? At least it is for John. I don't know about the rest of you. So an iterator represents a position in a sequence. It's really no more than that. Well, no, it is more than that. But at a sort of first approximation, an iterator represents a position in a sequence. As we saw on the previous slide, we obtained two iterators, one to the first position and one to the end. And again, as we just saw on the previous slide, iterators are generally used in pairs. We say where we want to begin the operation, where we want to end the operation. And we iterate over the container, over the range, from the first one until we get to the last one. First, if we have these pair of iterators, the things you get from begin and end. The first iterator points to the start of the range. It represents position 0 in your, if it's a sequence container. Represents the first element of the array. And the slightly tricky thing, which, well, the thing that you have to keep in mind, you get used to it pretty quickly, is that when we have these iterator pairs, the second iterator points to one position past the last element. You're not convinced with this, Sard?
No. It's really greedy.
So mathematically, this forms what's called a half-open range. We include the first position, we don't include the last iterator. Up to, but not including the last position.
Why was it implemented like that?
Because it makes it really easy to represent an empty sequence. Okay, so if you call begin, if the container is empty, if you call begin and it returns you something that's equal to end, so your first returns an iterator to one past nothing, sort of abstractly. It makes it easy to represent empty sequences. It also makes various algorithms easier to implement when you do it like this. So as we've already seen, we can obtain the beginning iterator, an iterator that points to the start of a container by calling .begin, the .begin member function, or you can use this freestanding function, standard begin. And again, there's a corresponding .end that gives you an iterator to one place past the end of the range. Now this is really important. Iterators are what we call value types. So if you've been following the course, I bang on and on and on about value types. I talk about value types a lot. And iterators are value types. That means that we can copy iterators. We can assign to iterators. And when we copy them, with one small exception, when we copy iterators, those copies are independent. So if you're confused as to what I mean by value type, think about an int. An int is a sort of canonical example of a value type. When you copy an int and you change the value of the copy, it doesn't affect the original. And in particular, one very important thing we can do with iterators is to compare them for equality. We could say, I have two iterators, are they the same? And they're the same if they point to the same position in the same container. So iterators all implement the operator overloads, the operator equals equals, and operator not equals. And they say, do I represent the same position in the same sequence? Iterators are small, for some meaning of small. Meaning, generally their size, the size they occupy on the stack, is usually about the same as 1 or 2 pointers. They're small objects. They're cheap, that is fast to copy, constant time copy. the STL algorithms, they all copy iterators around freely everywhere. So if you're constructing iterators, don't worry about it too much because it's not a slow operation. Right? Iterators are small and cheap and fast. So let's have a little look. Here I've got another vector, this time containing just 1, 2, 3. Get an iterator that points to which position? I've heard someone say it, yes. The 0th element. In C++, for obscure reasons, we count from 0. And you can get into holy wars about whether it's right to count from 0 or to count from 1, but in C++, 0 has 1. We count from 0, so this is an iterator to the element in position 0. And we can copy iterators. So I've created another iterator called it2 that is a copy of it1. I've used auto here because spelling the names of iterators is takes a lot of typing. It's quite a horrible thing to do, but luckily auto in C++11 saves us from all of that. If you can just do auto it1 equals vec.begin, you don't have to really worry too much about what the actual type name here is. I can tell you what it is, but it's, you don't have to worry about it. You can just say auto it1 equals vec.begin. And we do the same thing here. Create a new iterator, it2, whose type is deduced from the initializer. The initializer, we're saying we want a copy of iterator 1. So now, iterator 2 denotes the same position in the same collection. Because it's a copy, right? So iterator 2 also represents position 0 in our vector, in this vector vec. And indeed, we can assert that it1 equals it2. Two iterators to be equal, they represent the same position in the same collection, in the same sequence.
When you're doing the equals there, it's probably worth mentioning, right, that is the position you're checking for equality, not the value.
Absolutely. They represent the same position in the same sequence. So they're going to have the same value. When you dereference them, they're going to have the same value, of course.
But if you change the value, it would still say they're equal.
So I guess you could look at it as to say the value of an iterator is its position and the sequence it belongs it is pointing into.
The memory address will be different.
The memory addresses of it1 and it2 will be different, of course, because they're two separate objects. And in C++, separate objects have distinct addresses, always.
Good question.
Yeah.
So if initially you did it on this container, and you could have done it1 is back again to the 0th element.
Yeah.
And then you changed it so the 0th element instead of being 1 is now 2. There will still be equality, right?
Yes, because they still represent the same position in the same sequence. So we can copy iterators, we can assign to them. So now I'm changing the value of it2. Remember the value of an iterator, we can think of it as being the position and the collection. So here, it's still the same collection, but we're changing the position that it represents. We're saying you now represent this phantom position off the end here. And indeed, we can assert that this means that the iterators are no longer equal. Yes?
If you make an iterator const, that would just mean you cannot change it, but you can still modify the element.
Correct. Yes. So, pretty sure I'm going to talk about this in a minute, but there are these things called const iterators. This terminology, I admit, is quite confusing. So we have something called, if you have something called a const iterator, that means that you cannot modify the element via that iterator. It's a read-only iterator. A read-only iterator would be a much better name for it, right? So when you hear the term const iterator, think read-only iterator. We can only read through this iterator. We can't write through this iterator. However, an iterator here is a stack object, and just like any other object we create, we could have put the word const here. We could have said const auto it1 equals vec.begin.
So you could have as well const iterator to object, the same object, and normal iterator to the same object.
Yes. Yes. Whenever you hear the term const iterator, in your brain go read-only iterator. It's what we should have called them. It's a better name because it doesn't have this issue of, okay, is the iterator itself declared const? That is, I cannot modify the iterator. I can't assign to it. See, this assignment here is modifying the iterator, modifying the value of the iterator itself. If I've got a const object, it can't be changed after it's initialized. And so that's an iterator which is const, as opposed to a const iterator, which is one through which I can only read values in my sequence. I can't change the elements of the sequence. I know, the terminology is terrible, right? And I'm sorry, what can I say? This is, yeah.
But how would you change values through an iterator? Otherwise pointing to a specific position in a container.
It's a good thing you asked that, and we will we'll get onto that right now, in fact. We can access the elements that an iterator points to by writing a star, an asterisk, followed by the name of the iterator, star iter. And this operation, it's another bad bit of terminology, I'm afraid. This operation is called dereferencing. So if we say star iter, then we can access the element at that position in that collection. And as I just mentioned, if the thing we get from writing star iter, if that's read-only, then we call it a const iterator, which, yes, is a bad name. It should be called read-only iterator, but what are you going to do? We can advance an iterator to point to the next position in the sequence. So if we start off with we call begin, and it points to position 0, then we can advance it to point to position 1 by writing ++iter. There's also a function called standard. If you don't like writing ++, there's a function called standard advance, which does the same thing. So just for fun, use a different container this time. This time we've got an array of 12 floats. So an array is a fixed size object as opposed to a vector, which is dynamically sized. You can add and remove elements from it. An array is fixed. It always contains exactly that number of things. It always contains, in this case, 12 floats. Initialize them all to 0. And then we, just as we did before, we obtain an iterator to the start of the container. It1 points to the element at position 0 in this array. You actually don't need any of this bit. I got persuaded to add it, and then we found out that it's actually unnecessary. Okay. So here, when we create it, it1 points to the element at position 0. And then we call ++it1. And having done this, we've modified it1, and it now points to the element at position 1. Remember, there are 12 elements in our array. Do this as well if we wanted to. There's a function in the standard library called standard next. And what that does is, given an iterator, it gives you a new iterator, which is one place past the one that you gave it. So it2 points to the element at position 2. It's important to note that this has not modified it1. It1 still points to the element at position 1. It1 hasn't changed. So people who are here just in our last session before Christmas would have seen this already. Perhaps somebody else can tell me what this for loop here, what is it doing?
Changing all the elements.
You were here. You were here before Christmas.
I've forgotten.
You forgot you were there?
No, I know I was there, but I've forgotten all the content.
At the back. Absolutely. It sets all 12 elements of the array to the value 99, or float 99. Okay, so you remember the way a for loop works. We first do the setup bit, and we check to see whether we have the exit condition. We run the body, then we do the increment step, then we check the exit condition, and so on and so on. So in our initialization step, we're creating this, what is this now, our third iterator. Now it's just called it. And the first thing we do is to check that we're not at the end of the, sorry.
Just for fun, try like printing the values of the first iterator and the last iterator.
Yes.
And it seems like the last iterator is pointing to some random value. It's taking the value which it just finds there randomly.
Yeah, so as we said, sorry, when we went over this a couple of weeks ago, I went into a bit more depth. But so the end iterator points past the end of the array.
Understand that one.
Yeah, so there is nothing there. There is no value there that you can look at, right? So if you try and look at that value, that's bad. That's what we call undefined behavior. And what that means in sort of C++ terminology is anything could happen. Your program is no longer a valid C++ program when that happens. So it's pretty scary stuff, right? Dereferencing an invalid iterator, an iterator that does not point to a valid position in a valid sequence, that's bad, right? So in your case, if you do it with a vector, what's likely happened is it's just tried to read the random junk at the end as if it was an int or a float or whatever. If you were to use a sanitizer, that would catch that. It would give you an error message. If you were to use the Microsoft STL, they have these things called debug iterators, where, again, it would print you a nice error message at runtime telling you what's gone wrong. Probably give you the exact line of code where you did it as well. Yes, plus plus. Yes. In this case, yes, it would output exactly the same thing. So the difference between the pre-increment, which is plus plus thing, and post-increment, which is thing plus plus, is that the pre-increment increments the iterator, and then returns the new iterator, or reference to it. Right. Whereas what it plus plus does is it increments the iterator, but it returns you a new iterator which points to the old position. Sorry?
So the first one moves both.
So if you do it plus plus, the return value of that is an iterator that still points to the last position. You have modified modified iter, but your return value is something that points to the previous position. doing it this way round, so that involves a copy being taken, which is, as I said, I said iterators are cheap and copying them is not an expensive operation, but hey, if you can avoid doing it, then you may as well avoid doing it. And you can easily avoid doing it by saying plus plus it instead of it plus plus. So this is exactly the same difference, by the way, as for the plus plus operator, the increment operators on an int. So if you have an int, do int I equals 0, and then int j equals I plus plus, then j is going to be equal to 0 and I is going to be equal to 1. Right? This is something kind of hard to do in a hand-wavy way. But the way it works for ints is the same way, or rather, the way it works for iterators is the same way it works for ints.
Is this the more idiomatic way of doing it on C++?
For iterators, yes, the preference you should prefer doing pre-increment, I guess. So this is a loop that sets every element to the value 99. Begins at the beginning, stops when it gets to the end, iterates over every element using this iterator. Can anybody tell me a better way of writing this these 3 lines of code? Yes? Exactly. So in C++ 11, so this kind of code was really, really common in older C++ code bases. Right? You'd see things that looked like this kind of everywhere, not with auto actually, but then C++ 11, we got these lovely things called range-based for loops. So you could just say for auto-ref f in :arr, and that would iterate. It would basically do all this for you. It would mess about with iterators kind of behind the scenes. But for you as the programmer, it makes your life much easier. You can just iterate over the entire container very, very easily using a range-based for loop. So rather than, if you're iterating over the whole container, prefer a range-based for loop. It's no slower, will generate exactly the same code, and it's harder to get wrong. So you may as well use the range-based for loop when you can. Can anybody think of a second other way of doing this? A while loop. Oh, yes, you could use a while loop, I suppose. Wouldn't really do anything different to the for loop, but there's a way to reduce this to 1 line of code. Does anybody know what it is? I haven't covered it yet, so if you've read ahead or there is indeed a standard algorithm that fills a container with a particular value, and that algorithm is called standard fill. So, yes, an even better way of doing this is to use a standard library, use the algorithms, call standard fill. Because then, not only is it less code, but anybody who's scrolling through in a hurry can just see, okay, we're filling this container with this value. They don't have to try and, well, in this case it's relatively simple, but they don't have to try and puzzle out what your for loop is trying to do.
Are those also optimized in some way?
I'm sorry?
Are those algorithms also optimized in some way?
They can be. So standard fill is quite an interesting one because for containers, certain containers of certain types, so a vector of ints or an array of floats, yes, you can do this very, very, very quickly using low-level operations. Memcopy, memset, bcopy, I can't remember all the others. You can really, really heavily optimize this operation, make it really fast. So standard copy is another good example of, you can write what standard copy does yourself with a for loop, but if you use the standard version, well, the standard library writers are very good, and they put loads of optimizations in there for you. So if you have a vector of ints that you're using with standard copy, you can just it'll call memcopy, which is the really low level way of doing this, of just blasting those bytes across, and it doesn't have to do all of this slowly stepping through. It's not really slow, but slower stepping through.
Probably something else worth mentioning is not only will it do that, depending on whether you've given it a specific architecture, like Intel's Skylake processor, it can actually generate things like AVX2 instructions. So rather than even calling memcopy, it vectorizes the operation. Additionally, using the algorithms is really good if you've got large amounts of data, because it supports, since C++ 17, execution policies. So you can call standard fill a parallel execution policy, and it will actually utilize multiple threads to go ahead and fill it, which is obviously faster than doing it on one thread. And many of the algorithm functions support that.
Yes, but do any standard libraries yet? Oh, the Microsoft one has got some now,
There's
hasn't
an
it?
implementation for libc++ coming up.
Oh, okay. Well, okay. That's yet another reason to use standard algorithms.
Last question.
Yeah.
So you call standard fill
Yes.
on the array, not the iterator, right?
No.
On the iterator.
So currently, the standard library, all the standard library algorithms take iterator pairs. You tell it where to begin and where to end. So I haven't got it on the slide, unfortunately. I should have put it on there, but you call standard begin, standard : fill brackets arr.begin, arr.end.
Understood. Right. So
Yeah. So
it
you pass it. So fill takes and the value that you want to insert.
Right.
So that's the way all the standard library algorithms work at the moment. There is work underway. It will be in C++ 20 to allow you to just say standard fill brackets arr, 99 to stop you having to type begin and end everywhere.
Okay. Second question is about greater than, less than operator overloading for iterators. Are they by default overloaded to say the iterator, in the example here, it1 is less than it2, where it2 is being moved on in the same iterator?
In this particular case, they are.
Right. An array being an array, right?
An array being what we call a random access container.
Right.
Or more particularly, these things are random access iterators. So random access iterator is one of the categories of iterator that I'm going to start talking about in approximately 30 seconds.
But if you do it greater than your parent index.
Yes. Yeah, it's you cannot yes, correct. You can't compare iterators greater than or less than. I believe you cannot compare them for different containers.
Oh, okay.
It's I believe, I'd have to double check, but as far as I know, that it's only defined if you're comparing two positions within the same container. Yeah.
With Phil, where does, like with the for loop, the body?
Yeah.
Where does the body go for the fill?
So fill takes 3 arguments. It takes the start iterator, the end iterator, and the value to insert. Yeah.
So say if you want to do print, like you want to do the cout within that fill, is that possible?
Not with fill, because fill just takes a value. There is a function called standard generate, which takes an arbitrary function, which you can do anything with. So you could use that. But probably if you just wanted to print every element, an old-fashioned for loop would be better. There is a function called standard for each, in which you can pass an arbitrary function that gets executed on every element.
Is it because they wouldn't know what the container contains, the type of the container, that you can't, there's no algorithm to just print out?
Mostly because why can you not just standard cout --vec? I personally think that you should be able to. There are lots and lots of libraries out there that provide this functionality. It's not particularly hard to write yourself. If you're a little bit comfortable, if you're comfortable with templates, you can write that yourself. You can write a print vec thing. But for printing, for printing, you can just do it with a for loop, or you can use this standard for each function. next week, I'm going to talk more about the standard algorithms. And I'll go over several of these simpler ones, like fill, like perhaps generate, find, count, for each, and give you some practicing using them yourself as well. It's 7:30, and we've covered last week's material.
With 2D vectors.
As in a vector of vectors.
You iterate on array bracket 0. Could you iterate on the outside containers?
Okay, so C++ doesn't have really a two-dimensional vectors. What it has is you can implement it. You can have a vector of vectors.
Yeah.
Okay, so what you do is you'd iterate on over your outer vector, and when you dereference the iterator, it would let you access each inner vector, and you could then iterate over that. So you'd end up having two nested for loops.
Yes, you've got a container in a container.
Yeah.
So could you compare one of the outside containers with one of the other? You could try and compare two containers, but they're inside the bigger container.
What do you mean by comparing containers?
Well, say greater than or equal to.
Do you mean comparing vectors, comparing iterators?
Iterators. Going back to the previous question.
I can tell you it is very rarely useful to say, is this iterator greater than or less than another iterator? It's it's very rarely useful. It is essential, and we do it all the time, to be able to say, are these two equal? Are these two iterators equal to one another? It's very rarely useful.
Because you can never go backwards. You can never reverse the iterators. You've always got to go from lower to higher.
Well, it turns out you can, actually, for some iterators. For some iterators of particular categories, you can have this extended functionality of going backwards. So far we've only discussed the really basic iterator operations. Comparing, copying, assignment, all of that, construction, comparing for equality, advancing, dereferencing. These are the really fundamental basic operations. But some types of iterators offer more functionality. And this can be, and the level of functionality that an iterator provides, we call that its category, the iterator category. So some of the standard library algorithms can only be called on certain categories of iterator. So if you try and call standard sort on something that's not a random access iterator, we'll talk about what that means in a moment. If we call standard sort on something that's not a random access iterator, you're going to be in a world of pain. Unfortunately, at the moment, you'll get a compile error, but not a very nice compile error. You'll get a couple of hundred lines of what we call templates view. It's horrible. And part of the work that's underway for C++20 is is machinery that will just give you a nice error message saying the thing you gave me is not a random access iterator. But at the moment, if you try, yes, it's rather unfortunate. You'll get hideous error messages, but sorry about that. So some algorithms are restricted only to iterators of particular categories. And other algorithms, well, if you give them a low category iterator, they'll do it one way. And if you give them an iterator that has more functionality, well, they'll use that functionality to do things more efficiently. Which is pretty clever, really. So C++ 14, 17, I think. I don't think they added contiguous in 17. Anyway, there are 5 iterator categories, and they form a hierarchy. So at the bottom we have what we call single pass iterators. These are divided into 2 types, input and output. So input iterators are ones you can read from, but not write to. Output iterators are ones you can write to, but not read from. I'll get on to what single pass means in just a moment. We have forward iterators, which can do all the things single pass iterators can do, and a bit more. We have bidirectional iterators, which can do all the things that forward iterators can do, but they can also go backwards. So just as we can advance an iterator to move to the next position, with a bidirectional iterator, you can move backwards through the sequence. So perhaps you can already think of algorithms that you might be able to do if you could move backwards through a sequence. And finally, the most powerful category are random access iterators. So these can do the things, all the things bidirectional iterators can do. Plus we can zip around anywhere in the container very quickly. So each category offers successively more functionality than the previous category. Count the italicized thing. So 1, 2, 3, 4, 5. Yeah.
Are they exclusive, or do they sort of?
They're a hierarchy.
Yeah. Okay.
Yeah. So these are the basic ones. Random access are the most powerful. Each level can do everything the previous level can do and a bit more. So let's talk about input iterators first of all. Input iterators are iterators that we can read from. They provide input. But input iterators have a really annoying limitation. They are single pass, which means we can only look at them, basically it means we can only look at the value once. Once we have passed that value, we can never go back to it. It may not even exist anymore. If you think about if you're reading some bytes that are coming in over the network, you know, once you've read something, then it's gone. You can't go back and say, oh, hang on, computer over there, what did you say like just a second ago? Sorry, I've forgotten. You can't do that. Input iterators, sorry. Oh, fine. Input iterators is a single pass. So the best example of an input iterator is this thing called an iStream iterator. So an iStream, if you've used, you will have used the IOStream library. So if you've used an IF stream, an input file stream, you can wrap a stream in an iterator, and it will, every time you read from the iterator, it will get you the next value from the stream. But once we've read that value, it's disappeared from the stream. So there are quite a few algorithms, despite this single pass restriction. There are quite a few algorithms, the basic ones, that do operate on input iterators. An example of that would be standard count, for example. So standard count, you give it iterators and you give it a value to look for, and it counts how many times that value occurs in the sequence. And for that, well, we only need to pass through the sequence once. So this works just fine with input iterators. And we have output iterators. These are very similar to input iterators, except we can't read from them. We can only write to them. We can write to them by saying star iter equals something. Right, if we're reading from it, we do something equals star iter. Well, we can't read from an output iterator. We can only write to it. Like input iterators, output iterators are single pass. We can't save an iterator. We can't save a position in a stream and go back to that position later because that's gone away as soon as we've moved on. It's gone away. So there's a corresponding O-stream iterator in the standard library. So this lets you, really very useful actually, lets you wrap a standard stream, file stream, a string stream, whatever kind of stream you like, wrap it in an iterator so that you can use it with the standard algorithms. So output iterators, most often they turn up as what we call as a sort of out parameters, if you like, sort of, in standard algorithms. So standard copy copies from one sequence to another. So you give standard copy the start of the source range, the end of the source range, and you give it an output iterator which represents the start of the destination range. And indeed, for standard copy, again, it's single pass, so the first two arguments must be input iterators, and the last argument is an output iterator. Iterators of higher categories, through which we can write, so i.e. not read-only iterators, not const iterators, we call those mutable iterators. Mutable iterators of higher categories we can use as output iterators. So that was input and output. They're a bit horrible, I've got to be honest. They're not very nice. Got to worry about this single pass business. They're kind of ugly.
But if you use the auto,
yeah,
then your compiler selects the appropriate one for you.
You can never select the iterator. The iterator category is a property of the collection of the range that you're iterating over.
It's all internal.
Yeah.
If
If you were to write your own iterator for your own container type, then yes, you would have to decide and indeed declare what category your iterator, what level of functionality your iterator provided.
How often are the one use iterator, one pass iterators? I mean, like, is it, from your experience as a developer, would you avoid them or they are necessary?
Well, these iStream iterator and OStream iterator are useful, at least for simple things when you're just writing some code to quickly try and parse a file or something like that. For sort of more serious code, I might be tempted just to copy the whole file into memory and then use a vector which has quicker operations. So the basic iterators, we have input and output. The next level up, the first level that's actually not awful to use, are forward iterators. When I say use, I mean write algorithms which consume, which I admit is not how most people use the term use iterators. So we have forward iterators. A forward iterator can do everything an input iterator can do. They are input iterators. Not in the sense of inheritance, but as we've said, iterators have this notion of duck typing. So if it does everything that an iterator can do, then it is an iterator. If a type does everything that an input iterator should do, then it is an input iterator. And everything that meets, and the forward iterator requirements extend the input iterator requirements. So by definition, every forward iterator is an input iterator. Except that they don't have this single pass restriction. Which means that we can store an iterator and we can read from that iterator later. That iterator is not invalidated simply by incrementing another iterator far away. Much better, much nicer. So there is a collection, container type in the standard library. It's called a forward list. It's a singly linked list. And if you think about how a singly linked list can work, you can only travel forward within it. So the iterator type for a forward list is a forward iterator, unsurprisingly, I suppose. Many, many standard algorithms require at least forward iterators. I've just picked one at random, which is standard unique. So at the bottom we've got input iterators, not very nice. Then we've got forward iterators, which are nice, nicer. You can move forward, you can do the things that we've discussed. You can move forward, you can read from them, and in fact, and additionally with forward, you can store an iterator away over here, and you can read from it later, which you can't do safely with input iterators. Now we start getting on to the more useful ones, the more powerful iterator types. So we have bidirectional iterators. Again, a bidirectional iterator can do everything that a forward iterator can do. So they are forward iterators. But we can also use them to traverse backwards through the range. Forward iterators, as the name suggests, can only move forward. Bidirectional iterators, you can move forwards or backwards.
I mean, on the forward ones, you can't do minus.
Correct. They only have an increment operation. They can only move forward. So just as to advance an iterator to increment an iterator, you say plus plus iter. You can step backwards. You can step a bidirectional iterator backwards by saying minus minus iter. It's probably unsurprising, right?
Just double checking. It will stop before it will go up, over the beginning.
No.
It will keep going? No, it won't.
Well, you have to check, am I at the beginning yet? If you're stepping back, if you're stepping forward, you have to check, have I got to the end yet? When you're stepping backwards, you have to say, have I got to the beginning yet?
It's not circular.
No.
Yeah, I know.
Yeah.
But I was just wondering, so it's like if you have like a for loop, yes, from let's say 0 up to let's say the last element, yes. So
You want to go backwards.
yeah.
So you actually use R begin and R end. That's the iterator that lets you go in reverse. If you wanted to do what you're suggesting, which I would never recommend because there's literally a separate set of iterators for going backwards. But if you wanted to do it, once you reach dot begin, do not minus minus, do not decrement it again. Do not do that again. You're now before the beginning. Don't do it.
So again,
But if
Yes.
you did that, you won't be including in your loop dot begin 0 index. You could stop it at 1.
Well, you couldn't make it terminate on equals.
It's not.
You'd say,
But while it does not equal.
You use reverse. This is precisely why you would use the reverse iterators.
Yeah.
You wouldn't try and do this.
It's not. It doesn't work both ways.
You use R begin and R end.
so the best example, the usual one that comes up when we're giving examples of bidirectional iterators is standard list. So standard list is a doubly linked list. Every node in the list has a pointer to the next element and the next node and the previous node. And so its iterators are bidirectional. You can step either way, one step at a time, through the container. Now, if you think about it really hard, Do we even really? Yeah.
So on a list, what's the back part from the first element?
Nothing. You can't step backwards from element 0, just as you
So
can't
if you are at
step.
element 0 and you do minus minus one,
That is undefined behavior. Is what Tom was asking.
you will just look at the items that are on the way.
In practice, it probably would be harmless to set it. It's strictly speaking, you'd probably be harmless if you also try and access it.
So that bidirectional one, if you say do a, I don't know if it did sort, it will pass. If you do dot array dot begin, dot end, array dot end, and then you pass the function. That's what it's doing. It's passing both iterators across to your function. Minus sort
For each, for example.
Sorry?
So for each, as you have a
Yeah,
function.
yeah. So okay, that was
No. So instead for each, you don't get an iterator, you get the actual element, you get a reference to the element.
You get a reference to two elements in some places.
Oh, you mean like sort with predicate?
Yeah.
Yes, but that's not an iterator either. It just gives you two elements.
The value of two elements to compare to say,
Yeah,
is
yeah,
this
yeah.
one greater than that? This value.
So that's
Or
not
less
what,
than-
that's
yeah.
not what we're.
No. There are not many standard algorithms that require bidirectional iterators. There are only a few of them out of the, I think it's, are they up to 100 now? Algorithms, it's certainly over 90 standard library algorithms. Not very many of them require bidirectional iterators. I found one which is stable partition. So that was bidirectional. Bidirectional, you can move backwards or forwards. Oh no, that was one other thing I was going to say. I got distracted by parves at the back. I was going to say about bidirectional iterators. If you think about it sort of really hard, do we even really need them? Do we need to step backwards? Because if we've got a forward iterator, we want to get to this position, well, we could just step forward till we get to the end of the container, reinitialize our iterator from the first position, and keep going till we get there. And that would be, well, it might work, but it would be horribly slow, right? Because if we had like 10 million elements that we had to iterate through just to get to position -1. So that's really why bidirectional iterators exist, is to say, well, you can get to this previous position really efficiently. It's possible to do it with a forward iterator if you try hard enough, but you really shouldn't. And that brings me to random access iterators. So random access iterators are the most powerful iterator category. They're the best ones. They're the nicest. They're the guys we really like. So a random access iterator, it is a bidirectional iterator, so you can move forward or backwards. But you can move forward or backwards arbitrary distances quickly. So a bidirectional iterator, you can move forward or backwards one step at a time. With a random access iterator, you can move forwards or backwards as far as you like within the container in what we call in constant time. It's a fast operation. It doesn't depend on the number of elements that you're skipping over.
So is there any disadvantage of using that one?
No.
So why bother with others?
Because you cannot write a linked list that has a random access iterator. It's just not possible. Right? The level of iterator that you get depends on your container implementation. Right? So if your container is implemented as a linked list, the best you can, a doubly linked list, the best you can do is to have a bidirectional iterator. Right? Random access iterators in general require that you've stored your elements contiguously in memory. Like a vector or like an array or like a string or like a deck, which does it nearly contiguously, near enough anyway. So what random access iterators let you do is they let you advance n places in the same time as you can without depending on the value of n. Let's put it that way.
But each element has to be the same.
Well, all the collections in C++ they have the same type. Yeah, we don't have heterogeneous collections. Well, we have tuple, but it's not really the same thing. It's not a collection type. So you could do this just by taking a forward iterator and calling n times. But again, this would be really inefficient for large containers. So if you have a container that has random access iterators, you can go from position here to position there really quickly, in constant time. It does not depend on how many elements you're skipping over. So random access iterators, they provide a lot of extra operators. You do operator plus to move it, so you can do iter plus 3, would advance it 3 places. Operator plus equals, operator minus equals, because all of this applies to moving backwards as well. And of course, the canonical example, the best example of a container with random access iterators is standard vector. Standard vector is generally the best for everything, right? Standard vector is just the best thing in the world. And one of the things that makes it great is it has these random access iterators, so doing things with it is really fast. Yeah.
So if a container, the type of iterator, not type, but the category of the iterator, how would you find out if you read up the manual for standard library?
That's one way to do it. There is a way to do it programmatically.
You get an error if you try to do this plus 3.
Yes, if you took a bidirectional iterator and you said it plus 3, that would give you a compile time error. It would say this operator doesn't exist.
Yeah.
But there is a way. There are these things called type traits. It's really not worth getting into now, but it is possible to ask your iterator what category, what level of functionality it supports, what category it is. Yes, read up on standard iterator traits if you really want to know the grisly details. Or don't, because you don't really need it. So yeah, it's useful to know about these iterator categories as an end user, as a consumer of algorithms, because then you know which algorithms you can call for your containers. Yes?
Just as an offshoot edge case, why wouldn't you want to have linked lists that have random access?
If you can write one,
but wouldn't you want to skip certain nodes in the list to move to the third one along? Wouldn't that be useful?
It'd be lovely, but you're not going to be able to do it without.
Because I thought the list would say, oh, this is the next node, or this is the location of the next node. So would you then be able to? You won't be doing it fast, but you still should be able to move along.
No, that's a good point. You can still do it. Yes, as I said here. You can advance n places just by calling plus n times. Right. But the problem is then, if I've got 10 million things in my collection, and I want to go from position 1 to position 999, whatever, I've got to do 99 million individual steps to get there. Whereas with a vector, because it's random access, I can just go from there to there straight away. I don't have to step over each value in the middle. I can advance arbitrary distances in the same time, no matter how great the distance. I can teleport, if you like. Yes, there was a very good one. That it was. Fortunately, it's a bit too much. I was really thinking about setting it for you guys, but I thought it's a little bit too much work. But it's a really good one that taught you the value of bidirectional iterators.
What day?
I'd have to look. I can't remember.
Is it the model?
Yes.
I think it's day 6.
Okay. Well, there you go. Yeah, do people know about Advent of Code? People who haven't listened to me ranting about it for the last few weeks. Yeah, so I took out the slide because, well, it's not Advent anymore now, is it? But there still is, this website called adventofcode.com, and it has loads and loads, or 25, one for each day, loads of really good exercises. Some of the later ones in particular, really quite head-scratching, taxing ones. Sorry? Well, yes, okay, yeah. Each day has the first task, and then it has an extension task. So there are 50 stars available if you finish all of the challenges. Really recommend, if you want to practice your C++, begin on day one and keep going, because they're really, really good exercises. And in particular, there is one exercise involving marbles, which is apparently day 6. Day 9, which can really teach you the benefit of bidirectional iterators. You don't have to do them in order. No. When it was initially done, last month, they released them one day at a time, but now they're just all there. So, standard vector is the poster child for a container with random access iterators. Pointer to an element of a C array is also a random access iterator. In fact, this is the reason why iterators have this funny syntax for advancing them and dereferencing them. It's because it's mimicking what C pointers do. So a pointer to a C array is, in fact, a random access iterator. It does all the things that a random access iterator is required to be able to do. So random access iterators are generally required by the standard library's sorting operations. So standard sort, stable sort, nth element, shuffle, several more. The sorting operations generally require random access iterators. I believe it's possible to write sort operations which only require forward and bidirectional, but I think they're quite a lot slower. Well, they will be quite a lot slower. So this is perhaps more detail than you really needed, but it's good to give you the nitty-gritty sometimes. But if you want to boil it down to sort of a few bullet points to memorize, there are 5 categories, 5 iterator categories: input, output, forward, bidirectional, and random access. When you use a standard library container, the documentation will tell you which category that container's iterators satisfy. And when you come on the other side, when you come to use an algorithm, the algorithm's documentation will tell you which category of iterator it requires. If you don't match them up, you're going to be in a world of pain. Sorry about that. We're trying to fix it. How was that? Yeah? Learn a lot. Excellent. Does anybody have any questions about iterator categories that I haven't already tried to cover? Yeah. Okay, so it means that when you're skipping forward n elements, it doesn't depend on the value of n. So if you think about the other way I said of individually stepping each place, if I want to go to position 50, that's going to take half the time it's going to position 100, right? Because I have to step through each individual one. So that's what we call a linear time operation. It depends linearly on the number of elements I'm skipping over. Right, so but for random, the key thing about random access iterators is that I can move the iterator from pointing to here to pointing to position 50 in exactly the same time as it takes to move from position 0 to position 10 million.
Yeah, that makes sense. I think I got 10 halfway through when you were describing it before.
That's perfectly fine.
Can you think of it as your data set is like with the random access iterators? Every element is the same size, and that's why it can jump, because it's a multiplication. With another collection, you have various different size of elements, so you have to go through one at a time, because you can't do the multiplication because it doesn't know where the 50th element is, because they're all different. They could be different sizes.
Yeah. Yes. Yes. That's a good way of thinking. Right.
Because if you it's not about their size, it's about where they are. So imagine if I had I had a little bit. Imagine I had some pieces of paper, right? And for a random access iterator, they're all just these little pieces next to each other, right?
They're all the same size.
So not necessarily, because you could just have some maps that tells you, oh, okay, well, they're all next to each other, but I know that the next one's going to be 10 bytes bigger, so I can just access it in constant time. You could implement that and still have constant time access, so it doesn't matter about the size. But the point is that you could say, okay, I want to see the 10th element. Well, there, that's it. But now imagine that I've just covered the table with pieces of paper, and on the other side of them, it says what the next one in the sequence is. So you have to pick it up, look at it, and it will tell you which one matches, the number on top of it. So that's next one. And you pick that one up. So they're all randomly dispersed along the table. That's obviously now I've got to go to each one to get to the one that's 50, right? Whereas they're all just next to each other. I just okay, where's the 50th one?
Okay. But you got to have some way of tracking where the 50th one is. Yeah.
Can you create a, so this is just a very, without knowing how linked lists work, can you create like a table then for all the addresses and the sequences in a linked list, so that could help you bypass going across? So you have this directory of the elements and the addresses in the linked list, and that way you can skip faster by knowing the sequence of the addresses, as long as the linked list is const and you can't add to it.
Then why would you not use it?
Because I thought the linked list could have different types.
No. All of the C++ containers are homogeneous.
Okay.
They can only contain elements of the same type.
Okay.
Yeah.
Is there such a thing as an output iterator?
An output iterator, yes, there is.
Did you cover that?
Yes. That's okay. I'll put the slides up. Yeah.
Just on this question of homogeneity.
Yes. Homogeneity.
Homogeneity. If you had a vector of stood array objects,
Yes.
each of which of those stood array objects happen to be of a different length.
No. No, because the
Have that, right?
no, you couldn't have that.
Because, right. So this means
Because the length of a standard array
yeah.
is part of its type.
Right. So that okay. So you have. So what I'm getting at is because does this mean? I'm sure there are exceptions to this. Does this mean that in an iterable type on which you have an iterator, all elements in that are of the same size?
They're of the same type, so they're going to be the same size.
And then no, you can't. There's no exceptions to that. I can't think of any offhand.
You can have a vector of vectors, and if I have two vectors in the outer vector, the first inner vector might have a length of 5 elements, and the next one might have a length of 10 elements. So
Right, because in a vector, it's got no notion of size as part of its type.
correct, it's not part of the type.
Yeah. Okay. Cool.
Any last questions? Going once, going twice, gone. Too slow. Let's talk about the containers. We talked about vector and list, a couple already. Let's have a bit of an overview. I'm not going to go into too much detail about all of them. Just going to let you know what I think are the most useful ones. Other people may disagree. So, as I mentioned many times, the standard library gives us several different containers which we should use in our programs. And there are four. I really shouldn't have used the word category again here. These are four blobs, four groups of containers. Well, sequence containers, associative containers, unordered associative containers, and a few container adapters. So sequence containers, elements are stored in the order that you put them into the sequence. Right? A vector, for example, stores the elements in the order you put things into the vector. Yep. Associative containers, on the other hand, containers that are sorted. They maintain their elements in a sorted order for you. The unordered containers, on the other hand, are not ordered. They use they're hash tables, basically, hash sets, hash maps. And finally, we have these adapters that don't get a lot of use, but I thought I'd include them for completeness.
What's a typical associative container?
Standard map, standard set.
Oh, so, okay.
Oh,
And the unordered?
unordered set, unordered map. Yeah, I'll talk about them in more detail now, in fact. So all of those standard containers are what we call class templates. I haven't talked very much about templates in this class yet, but basically a template is like a blueprint for how to make a class. So, as we've seen several times, when we create a vector, we tell it the element type in those angle brackets. Right, so vector is a class template, and we can say, okay, we've got the blueprint for creating this vector. I want you to make me a concrete vector of ints, and that's a vector of ints, and it's a different type to a vector of floats. And it's a different type to a vector of strings. And this means that when we create a vector of ints, all of the operations are specialized just for ints. And this is one of the things that makes C++ really, really fast. Is that the compiler, the optimizer, can work on this function. You know, these functions are specialized just for the type that you instantiate the container with. Just for the type that you are putting into the container. So if I were to talk about templates, I could do, probably, I don't know, many weeks talking just about templates. Not going to go too much into it today, but if all you remember is that you have to provide the element types inside the angle brackets, that's because these things are class templates. We have to give them the type that we're operating on. Well, the other thing worth remembering is that, as I said, a vector of ints is not the same type as a vector of doubles. This means take my vector blueprint and construct a vector of ints from that blueprint. Construct a vector of doubles from that blueprint. But the thing you make from the blueprint are not the same types.
Will you get into trouble if you make the vector of ints and one of unsigned int? So the compiler notice these are not the same thing?
It will know they're not the same type. Yeah.
You can make vector of ints.
Yes, you can have a vector of ints, you can have a vector of a list of strings. You can nest these things if you're particularly sadistic or know the other one. Anyway. We can also, again, I'll put this in mostly for sort of information if people want to go and do a bit more reading themselves. You can specialize the behavior of these containers in many ways by providing template arguments. So you can customize the hash function that's used for the unordered containers, for example. And you can also specify what kind of memory allocation you want to do. Again, these are pretty advanced things, and I wouldn't worry about that too much right now. But it's nice to know that these things are possible. Right? In particular, not many languages let you customize memory allocation. So again, it's one of the reasons that C++ gets a lot of use in domains where really fast performance is required. Games and an awful lot of the stuff they do here, I suspect. Some people might disagree with this, but for the most part, the containers are designed to have a consistent API, a consistent interface for programmers to use. Reasonably consistent. So for example, vector, list, and deck, they all have a member function called pushback. And what pushback does is it pushes a new value into the back of my sequence. And in particular, all of the containers have these begin and end member functions that we were talking about quite a long time ago. And they return iterators. What kind of iterator, what category of iterator they return, well, that depends on which particular container you're talking about. As well as these begin and end member functions, we have cBegin and cEnd member functions. These return const iterators. Remember, const iterator provides read-only access to the element. So if you go to this link, well, I mean, not now, but if you look at the slides later, you'll be able to click that link. It's got a nice, well, quite large table of all the containers and all the member functions, and it shows you which containers have which member functions. And it's quite cool. Somebody must have spent an awful long time putting that together. And in general, actually, CPP reference it's like the Bible for C++ programmers. If you haven't found it yet, it's generally the top of every. If you Google search for anything related to C++, CPP reference is generally near the top. But it's like the Bible for C++ programmers. And it's a bit sort of, can be quite technical. Sometimes it's very, very pedantically correct. But yeah, it's a very, very useful site. And yes, if you go to this URL, it'll tell you what all the containers are. And you'll be able to click all of those, and you can go into the details of exactly what all the vector member functions are, and the complexity guarantees for all the vector functions, and whether those member functions invalidate your iterators. And it's got all the details of everything. So CPP reference, if you haven't found it, well, you must have, because you've almost all been coming to this course for a while, and you've probably Googled things.
It's a bit heavy duty.
It's quite heavy duty, yes.
The other one's a bit easier to understand, the C++.
C++.com. Yes, that is the other reference site. It's a bit less dry, sometimes a bit more approachable in some ways. Where did you find that?
Just over there.
Wow. I should have given you all a break, shouldn't I? Anyway, never mind. All right, so we had 4 groups: sequence containers, associative containers, unordered associative containers. The first group, sequence containers. So of these, we've got standard array, which we've talked about earlier. It's a fixed size random access array. You declare up front how many elements this array will have, and that's it. That's how many it has. You can't add elements to an array. You can't remove elements from an array. It always has exactly the number that you give it. And in fact, the number of this is a class template again, and the number of elements it has is part of the type of that object. Next is standard vector, our best friend. As you all know by now, I'm sure, it's a dynamically sized random access array. This means that you can add things to the end of a vector, you can remove things from a vector, you can change the size of it. It's great. A standard list, already mentioned it, it's a doubly linked list. You can move forwards and backwards within this list. As opposed to a forward list. This was added in C++ 11, and I'm not really sure why, because it's not particularly useful as far as I know, but maybe I just don't have enough imagination. But now there's a singly, have I spelled singly right there? Does it need an E in it? That doesn't look right.
Probably does.
It didn't get underlined when I was writing.
It looks like singing.
Yeah. Anyway, it didn't underline it when I was writing. So.
It's valid. It's a valid word.
Singly linked list. Anyway, singly linked list. So you can only move forward through the list. And there's this thing called a deck. It's a double-ended queue. And then it's not really a sequence container, or at least it's not included in that part of the standard document. But to all intents and purposes, a standard string is a kind of sequence container. You can think of it as like a vector that's specialized for holding characters. Yes.
Can you use standard array as a replacement for sequence?
Yes, you can and you should.
Pass them into like C functions.
Dot data gives you gives you dot data gives you
If you call a C function, you use dot data to point to dot size.
So I'm not familiar with the deck. Where would you use the deck?
Don't worry, I'll talk about that in just a moment. Oh, I thought you were bringing me coffee, Tom. Oh, thank you anyway. Water with a lid anyway. Thank you. First of all, let's talk about our best friend. Let's talk about standard vector. Somebody's got the right idea. Yes, absolutely. Yay, standard vector. We love it. It's a dynamically sized random access array. Element access is constant time. I can ask the array for element. Sorry, I can ask a vector for the element 1. I can ask the array for element 99. I can ask the vector for element 10 billion. And it will return all of those things to me in the same time, no matter which position I asked for. It's a constant time operation. Adding elements to the end of an array is a constant time operation. By the way, I did have a slide prepared about algorithmic complexity, and I decided to skip them because I thought we had enough for today. So I was going to explain these terms in a bit more detail, and if people want me to, I can do that next week. It's up to you guys. Let me know on Slack. If you're not on Slack, well, you don't get to have a vote. Adding elements to the end of an array is, so basically, accessing elements is fast. When you see constant time, think fast. Accessing elements of a vector is fast. Adding elements to the end of a vector is fast. Adding elements anywhere but the end of a vector is not as fast.
You can't have the pointers to elements of vector.
Why not?
The element of the vector, not to the vector, the whole vector, to the element of the vector.
You can have a pointer to an element of a vector if you want to, but you have to be very careful because whenever you add new elements to a vector, it might reallocate its internal memory.
So should you actually consider this even as a body option? Like okay, so if you have the, let's say, 5 elements, let's say you add 6th element,
Yeah.
and it reallocates.
Yeah.
You had the pointer to element 3, and now there's nothing there.
Yeah.
So should you even try? Would that be safe?
It's not safe if you try to read from that pointer.
Yeah.
But that's no different to if you had an iterator that pointed to position 3, and then you add something to the end of the vector internally reallocates, moves the storage from here to over here, and now your iterator's pointing to nothing.
So in real life, would you
And
avoid that, or?
well, it's something you have to be careful of. It's the thing about iterator invalidation. In general, if you're holding on to iterators into a container, doing things to modify the size of that container, in general, is something that you have to go, oh, hang on, is this okay? Right? And the way you find out whether it's okay is by going to CPP reference and you click on the member function and it will tell you this may invalidate iterators, or this will invalidate iterators. And if it says that, you go, okay, well, this is not a good thing to do. But if you go to list.pushback in the documentation for a standard list, this will say, this function does not invalidate iterators. And you go, okay, for a list, this is fine. It's safe.
But you can reallocate after you get out of scope.
What do you mean reallocate?
So you can just reinitialize the iterator.
Yes, exactly. You can, yes. And not pushback, but actually there's a function called vector.insert that will return you a new iterator. Anyway, yeah. So we already said iterators are random access. In fact, in C++ 17, they're guaranteed to be contiguous. They were always contiguous, but now it's actually guaranteed. Standard vector should be your default go-to container for pretty much everything you do. Right? Have I mentioned that I really like standard vector? Yeah. I don't think I've mentioned it enough. When in doubt, use vector. Right?
Contiguous, guaranteed.
Okay, the contiguous bit means that it is guaranteed that all of your elements are stored one after the other in a sequence in memory. Right? And this is the thing that makes vector as fast as it is.
But wasn't it already happening?
Yes, it was, but now it's guaranteed. Technically it wasn't guaranteed, but now it is. Yes, this has always happened since the beginning of time, but now the standard actually says it must happen. Yeah.
If I use a vector but do not make use of properties that differentiate it, for example, from an array, does it compile to something else, or is it?
No, when you create a vector, you say I want a variable of type vector of int, say, then that variable has type vector. Is that what you were asking? I'm not sure.
Yeah, I was wondering, for example, if I know that, for example, I don't need dynamic size of a vector, whether I would benefit from additional performance if I just use standard array.
Sometimes you can. Yes. The difference between an array and a vector is not purely the fixed size. The vector allocates its elements on the heap. It goes away and asks the operating system, can I have some memory, please? And then stores the elements in that memory that it gets. And that process of going away to the operating system and saying, can I have some memory? That, in some circumstances, if you're writing really high performance code, that can be something you want to avoid. That's why they have this allocator parameter that I was talking about. They customize how you do this memory allocation. Whereas an array, because it's a fixed size, it just stores it in the object itself. Right? It doesn't have this other free storage over there that it actually uses. It just stores the elements in the object itself. So this means that you shouldn't use an array for anything that's too big. If you've got millions of elements, don't put them in an array, put them in a vector. Because if you're putting an array on the stack, then you have a limited amount of space to play with. I don't want to get too much into it, but yeah. Basically, use an array when the number of elements is small and known, fixed, known at compile time. If it's fixed and small, use an array. Otherwise, use a vector.
Let's say I had a data set recently, and it was 12 million elements sorted over 250 columns. So let's say I wanted to perform some summary statistics on that.
For 12 million elements, yes, use a vector. Do not use an array. You will.
Can't you help yourself out by using reserve as well?
Yes. So an optimization really, and if you're not careful with how you use it, it can be a pessimization. Some of the leading experts actually say don't use it. But yes, you can upfront, if you know how many elements your vector is going to end up having, you can reserve that much memory upfront using a function called .reserve. Because the way vector works in general is that so it starts off empty, you put one thing in it, it goes off the operator system, so it can have some memory. Okay. When you reach the end, when it's full, it goes off and it asks for twice as much memory as it had before. Right? So if it had 4 elements in and that's full, it'll go off and allocate, malloc, reserve. Everyone's making me jealous now, Oliver.
Maybe we should have a break, like 3 minutes.
Maybe we should have a break. Yeah, why not? I was going to, yeah, why not? Since you suggested it. I have been waffling for a very long time.
So 3 minutes or no break?
Yeah, I mean, we're only going till 9, right? So just a very quick break.
You want coffee or something?
But it seems like everybody's a bit phased.
No, it's nice. So, but you should be careful. You should look up.
Anything that's template, any of the containers, all of the containers are templated, and you have it at the same time. Now, you can achieve the same effect by, say, you could implement a base file, and your container will hold pointers to instances of the base files, or a reference wrapper. If you want the container to own it, you have to do something like this. But essentially, you have a vector of some interface. You can then create however many implementations and compare it to that.
So let's say for the sake of argument, I've got a situation where I need to mix 2 integers and a set of strings in an array in a vector. Yeah. So let's say for the first one.
So some of the elements will be strings, some will be it.
Yeah, exactly. So let's say for the sake of argument, the first element, the first bit will tell me how many strings there are in there. The second element being the index pointing to a particular variance.
So understood vector, understood variance, and varied will be templated on string. So then for each element, I can then visit the element, the variant in that particular index. And if it's a string, it will execute my handler it's a string. And if it's an int, it will execute my handler for it being an int. So you use the visit assign the visits to that. You could write your own class and use something like a union. But what I suggest is have your containers understood vector is a variant of int understood.
Anyway,
string operation, so good.
I think he's got quite a lot of licenses. So it's just a question of having renewing it for the question. Someone else. Oh, Christmas. Yeah. What was the party about? No, we just did that. Oh, okay. He was taking Nicky down there.
Are we feeling refreshed? Yeah. I didn't realise there was a break room right there. Otherwise, I'd have paused earlier. But
God, should I finish chewing these peanuts? Everybody's really enjoying Bloomberg's hospitality.
Hey. Haven't given us pizza apart from one.
Minecraft.
So Freudian slip.
Okay,
Minecraft.
almost everybody back, and I haven't got very long left anyway. Can't really remember where I was, so we'll just carry on and say vector should be your default container that you use for your default go-to container that you should think about using before you use anything else. I like vector. You should like vectors. There are other containers. There's standard list. Standard list is a doubly linked list. So hands up if you know what a doubly linked list is. 1, 2, 3. Ollie? What?
Yes, sir. Yes.
Right. Your hand wasn't up. Okay. So a linked list is one of the classic data structures that if you go and do like a computer science course, this is what you'll learn like in your first few weeks. It's about this data structure called linked lists. And linked list has a node, and each node has the address of the next node in the sequence. So I can't remember who made this analogy. It might have been Parvez. But did you mention the postman?
It was Ollie in his
What was
terraced
it?
houses. Yeah.
Oh, sorry. So I like this analogy of the postman. So imagine there's a postman who has a stack of mail to deliver. And on a normal street in a vector is like a row of terraced houses. It's really easy. Postman goes to the first house, goes to the next house, goes to the next house, goes to the next house. All he has to do is walk straight down the street. You can even chuck the letters through the letterbox because he's a really good postman. Right? Postman Pat. He's better than Postman Pat.
He's Jeff Bezos.
He's, Anyway. The vector's like a row of terraced houses. Really easy to go from one to the next. Really fast. A linked list is like, I have a stack of mail to deliver, and in order to so I go to the first house, and I hand them their mail, and then I say, okay, where do I go next? And they'll say, well, you go to this address right over town. I say, okay, right. Trudge all the way across town, deliver this piece of mail, and say, okay, where do I go next? And they'll say, oh, well, now you need to go like 3 miles south. All right, 3 miles south. And then I say, well, where do I go next? Well, now you've got to go back really close to where you started, but not the same place, just quite close to it. So now I've trudged all the way back another several miles over there. Right? That's what a linked list is. It's a lot of separate addresses all over the place, where each of these addresses contains the information about what comes next in the sequence. And just by that analogy, you can already see that iterating over a list is going to be slow, because I have to trudge from one address to the other, to the other, to the other. Whereas with a nice row of terraced houses, I can just walk down the street. And just to take things back to talking about computers, this means that for a vector, it's one of the reasons that vector is brilliant, because the nice row of contiguous addresses is very, very cache friendly. CPUs have these big, these days, big memory caches. They can sort of guess what you want to do. They speculatively almost load up from main memory into the CPU cache. And for a vector, it can see very quickly, okay, you're just going over every element. I'm just going to copy that across from main memory into the CPU cache, iterate straight over it. Really easy. Really fast, really fast. For a list, it doesn't know what the second address is until you visited the first address. It doesn't know what the third one is until you visited the second. you have to trudge all the way over town. The postman has to trudge all the way over town. When in the computer terms, the computer has to fetch a value from this bit of memory, and then from a different bit of memory over there, and then from a different bit of memory over there. It can't predict the access pattern. You don't have any benefit from caching.
Can I ask a silly question? What would happen if we would create an index of those addresses? So they are still in the random place, but we have like an index where they are.
Okay, so that's like the postman has a clipboard, and it says, well, first you need to deliver here, but then you still need to go to the other side of town. I mean, it saves him having to ask the person who lives at house number 1,
Yeah.
but he still needs to jump all over town. So it's still going to take a lot longer than just walking down the street.
Yeah, true. But what I was thinking, like if you have the index, yes, where you go, then you could, for example, sort and say, so by.
Okay, but the addresses here represent like addresses in computer memory. You can't really, you know, where you're. Yeah, well, not even that a clever malloc optimizer implementation or a clever allocator.
But even then, you've got this case of there's obviously minimum size you can pull into a cache line. So depending on the size of your elements, whether or not you get benefit is questionable. So ideally, you want things to be cache local. Use a vector.
What's the example?
10 to 9.
Yes. Example of right. So, okay, I've just said linked lists are rubbish because you've got to, you know, our postman has to go to house 1. Okay, what's house 2? What's the address of house 2? He asks. He trudges all the way over town to go and deliver the second letter. Trudges all the way across town again to deliver the third letter, and so on. This is a bit rubbish. Why would these things even exist? Right? This is terrible. And the reason they exist is because inserting a new link in this chain is really easy. Right? Inserting a new link into the middle of our chain is really easy. What we need to do, all we need to do is visit house number 3 and say, okay, for the next postman that comes along, direct them to this address. And then we go across to that address and say, can we tell them to, when the postman comes along, tell them to deliver to the one over there. So inserting a new link in the chain is really fast. Adding or removing an element anywhere in the list is a constant time operation. For a vector, adding a new element on the end of the array is a constant time operation. It's fast. Constant time, remember, constant time is fast. Right? Adding a new element on the end of the array is fast. Now think about it. We've got a row of terrace houses. All we have to do is build a new house on the end of our terrace. If we want to insert a new house in the middle of our terrace, what do? Well, that's a lot more difficult. We have to knock down half our terrace houses, build a new house, and then rebuild all of those houses. And that's slow. So that's more or less well, it is really the only advantage that a list has over a vector. You can insert anywhere into the list quickly. But accessing a particular element is linear in the number of elements that you have to go through. So in order to get our postman is round, in order to get to house number 50, he first has to go to house number 1, which he knows the address of. He has to find out the address of house number 2 from house number 1. He has to find out the address of house number 3 from house number 2. He can't just skip straight to house 50. He has to go through and ask each house in turn in order to finally find where element 50 is, where house number 50 is.
Like a treasure hunt.
Like a treasure hunt, yeah. Whereas for our postman, he doesn't have to bother with that. He can just go, okay, each house is that far wide, so I need to go 273 meters down the road. And there he is. I'm not even sure why I bothered making a note of this, but it's one of the changes that was in C++ 11. You can actually access the size of the list in constant time. So the postman knows how many houses he has on his round altogether. He just still can only visit them in order. So for a doubly linked list, iterators are bidirectional. So in our analogy, I've said that each house knows the address of the next house. In fact, in a doubly linked list, each house knows the address of the previous house in the chain as well. Right, so it's a chain of links, a list of links, a linked list. And it's doubly linked because each house knows the address of the next one in the chain and the address of the previous one in the chain. So this means if he wanted to, if he knew the address of the last house, the postman could do his round backwards. Wouldn't be any quicker. He'd still have to dart all over memory, all over town to deliver his mail. But it means that the iterators are bidirectional. We can move backwards through the list. Another downside to standard lists is it's node-based. Every time you add an element to a list, an allocation happens, which again is not something you really want to happen. So as a guideline, the only reason that you would consider using a standard list is because you are frequently inserting or removing elements from the middle of a large sequence. Right.
Would you ever consider generally inserting and removing and converting into a vector to do that?
That can be a valid thing to do. So when you're construct it as a list and then copy it into a vector. Yeah. Can be a valid thing to do. I'll just talk about deck and then we'll wrap up. So deck's a funny thing. It's a double-ended queue. I'm going to stop talking about postman now, mostly because I don't know how to represent a deck as a thing a postman visits. But a deck's a really strange kind of data structure. It's a double-ended. It's like a vector that's fast to put things on either end. So element access is constant time. Insertion or removal at the end or the beginning of a deck is constant time. So for a vector, inserting at the end was constant time, was fast. For a deck, insertion or removal at either end is fast. Insertion in the middle is still slow. We've still got to knock down a lot of houses and rebuild them. But inserting at either end is fast. Why? Because it's very cleverly... no, and I'll talk about why that is in...
Two vectors stuck together.
It's basically implemented as a vector effect. That's kind of what you don't really need to know. So standard decks, iterators, and random access. It's not contiguous, not wholly contiguous. But the iterators are random access. So we can use it in all the algorithms that require random access iterators, all the good ones, all the sorting and nth element and all those. Basically, you can use it with every algorithm. So here's a funny thing. I've said vector is wonderful, and vector, I've been singing its praises all night. Vector's the greatest thing since sliced bread. In fact, it's better than sliced bread. I can slice my own bread. I can't write my own vector. But vector's brilliant. And yet, standard deck offers all the same complexity guarantees, but we've got this added facility that we can put things at the beginning in constant time, quickly. So why would you ever use a vector then? Why not just use a deck everywhere? And the answer is a little bit subtle and really goes into talking about these what we mean by algorithmic complexity and what we mean by these complexity guarantees. So inserting at the beginning, or at the end, sorry, let's say, inserting at the end is a constant time operation for both a vector and for a deck. But that just means that it doesn't depend on the number of elements that we already have in our container. And as it happens, this operation is it's very likely to be quicker for a vector than for a deck. All of these operations are going to be quicker for a vector than for a deck. The only thing a deck is going to be quicker at is inserting at the beginning. Right, so on paper, if you look at it, if you only look at the algorithmic complexity, you can say, oh, well, a deck's like a vector, but better. Well, it turns out it's not really. It's better at one thing. And if you do that one thing, then by all means use a deck. Because if you're using it as a double-ended queue, that is, you're popping things in one end of the queue, pushing things in one end of the queue and popping them out the other, then that's what a deck is for. Right? But if you're only ever inserting at the end, use a vector, because that's what a vector's for. Right, that is just about all I have time for. I did have an exercise that I was going to give you, but I'll put the slides up on the fact that we haven't got to it's quite good, because it gives me a chance to add a bit more to make it your homework as well. So I'll put it up on with the slides on the GitHub, and again, really encourage everybody to come along on Thursdays to the workshop sessions and work on the homework. Thank you, everybody, for coming, and thank you very much to Bloomberg for hosting us in this rather superb environment. It's been great, and yeah, see you next week, I hope, although we're not quite sure where yet.
Okay. Thanks so much to Tristan for a really wonderful class. So, two things. First one, can you please make sure that place is spotless clean, so we don't want to get in trouble. Second thing is, we are going to not do pancake because it's a little bit too far, so we will go to sugar loaf, sugar like a sweet and then loaf. So it's just behind the corner. You're very welcome to join us. If you thought that the class was fantastic, make sure these two guys, they are hydrated and fed before we send them home. Yeah, and I hope to see you on Thursday or Tuesday. Thanks a lot, and thank you very much for Bloomberg. Really appreciate it.
Cheers.